Chapter 15 about altering product strength. I love this chapter, but some of you, there's a fair amount of algebra. Today's lecture is kind of the algebraic method. So we're going to go through and solve a bunch of dilution and fortification questions using the algebraic method that I'll talk through. The good news is there's an alternative way for doing a lot of these concentrating, diluting things using the alligation method. And that will be next week when we'll talk, or the next lecture would be on the alligation method. But I will just say this tends to be, I think, one of the more difficult sections for that. But with that, let's go ahead and get started. And again, I want to just clarify a couple of things. While all that's listed here, these are really the main things that we're going to be doing today, is doing the calculations on dilution and fortification. Those other specific things aren't as important. So remember, today is dilution and fortification. All right. So with that, let's do just a couple of definitions here, and I try to do some artwork to help you illustrate that, but I would please appreciate if you would not refer to these illustrations as a toilet. That's not the idea. They're beakers with drug in them, all right? So don't get the wrong idea with my artwork. So having said that, what we're starting with is the idea of dilution. So if we take dilution, this is an important idea, is that the little brown pieces of drug in the beaker represent drug. The mass of the drug, the amount of the drug. The liquid around that drug represents the volume. And remember, concentration is an expression of the weight or the amount of mass or drug in a certain volume. So in this beaker right here, if we start here and then do what? What did we do? We didn't change the amount of drug, but we increased the amount of water or the volume of the diluent around there. We are diluting it. And the idea here, and this is what's really important, mass is unchanged when you dilute something. You have the same amount of mass before as you do afterward. The mass doesn't change. The only thing that happens in dilution is that the volume around that, the concentration changes because the volume changes, not the amount of drug, not the mass of the drug. All right? Now, concentration, and the reason I would say this is a little less important, there are not going to be a lot of examples of this, because this is going the opposite way, where, again, mass of the drug is in change. What happens is the amount of drug is the same before and after, but what you do is you remove the diluent. You remove the liquid around that, which is not really all that possible. You could heat it, you could evaporate it, but in pharmacy, we don't normally concentrate by keeping the drug the same and just removing diluent. We usually concentrate things by adding more drug to it. So the point is, that's why I tried to emphasize before, this is really important for understanding dilution and fortification, because in fortification, unlike concentration, what you're doing is actually increasing the mass of the drug. So here the mass of the drug is increased, whereas here we said it was unchanged, all right? Those are the key differences, all right? We're going to make sure that you understand when we fortify things, the mass is changing, it's increasing. When we dilute something, the mass doesn't change, the concentration changes. All right, not the best artwork in the world, but hopefully that'll make sense. So let's focus on dilution, all right? To do these formulas, we're going to start on dilution. This is also very important, this slide here and these terminologies, because you need to understand what C will be used in our formulas, C, Q, and M. C stands for concentration, Q stands for quantity. Now, in a lot of these times when we're doing liquids, you can think of the volume as the quantity, but you can do these with semi-solids where you have weight instead of just volume. So that's why we say quantity, but quantity could be analogous to volume in a lot of these calculations. So we have a concentration, and again, a concentration would be something like in milligrams per mil, where a quantity would be something like a volume, like milliliters. This is important than mass. The formula for mass of something is the concentration times its quantity. So C times Q equals M. Mass is equal to the concentration times the quantity. And just use our sample units. If you have milligrams per mil times mil, mils cancel, right? And what do you get? You get milligrams, you get mass, you get weight. So remember, a concentration times its quantity gives you a mass, all right? Now let's put some numbers by it. So again, in the dilution thing, the concentration and the volume of the solution I have to begin with, I'm going to put as C1, Q1, okay? So that my original solution will be C1 and Q1 for the original concentration and quantity. Therefore, when I multiply those together, that's equal to the mass one. The mass of my solution is equal to the C1 times the Q1, all right? Well, what happens after you do something like diluting it or concentrating it? Again, the mass doesn't change when that happens, but you have a new C, you have a new concentration, and you have a new quantity. So you have a new C2, Q2, but in the end, that's those two times together is a new mass. So you've got two different masses. And what we're saying in dilution, that the mass doesn't change. So M1 equals M2, In a dilution or a concentration, regardless of what you do or amount of water you add or subtract, the mass of the drug doesn't change. So M1 will always equal M2, which means that your C1Q1 will always equal C2Q2. And this is the key thing. You got to know this. This is what's going to be the basis for all of our calculations here in a minute for the dilutions. Okay? Easy enough? You seem bored already? That's okay. Let's see how you do. This is a pretty straightforward question, application of dilution, all right? And it says, how many milliliters of a 10% weight per volume stock solution of a substance are needed to prepare 120 milliliters of a solution containing a different concentration? And that concentration is 10 milligrams per mil, all right? So what do we want? We want to make a solution that has 120 mils and a concentration of 10 milligrams per mil. And to do that, we need to use some volume of our 10% weight per volume stock solution, all right? So this is really important. You must, this is step one. For all of these calculations, do this first. Remember, you need to set your C1 and Q1 and establish your C2 and Q2. Do not try to do any math until you've labeled your values. You've got to establish those values. So looking at this question, it said how many milliliters? So do we know the quantity of our 10% stock solution? Or is that what we're solving for? We are solving for the quantity of our 10% solution. So since this is how many milliliters, that's what my Q1 is equal to. I do not know what volume of my 10% to use. I'm solving for that. So I'm going to set my Q1 equal to X milliliters. I don't know it. But what is the concentration? It's a 10% weight per volume concentration. So I know it's C1. The C1 is 10%. The Q1 is X milliliters. I do not know how many milliliters. All right? So far, so good on that? Now, what are we trying to prepare? What we're trying to do is use that solution to make something else. We want to prepare 120 milliliters of something. So what we're trying to do, our target Q2 is 120 milliliters. So that's where that comes from. And what do we want our final concentration to be? So our C2 comes from over there, 10 milligrams per mil. So do you see the first thing to do is to take the question and establish what your C's and Q's are. C1, Q1, C2, Q2, and use the question to establish what you're trying to make. Is there any questions at this point? That is the first step for every single question we're going to do today, all right? The problem now is you have to look at your units. You need to make sure that your Q's and C's have the same units. So if you look at the units for my Q's, are those both in milliliters? Yes, that's okay. They need to be in the same units before we calculate mass. So milliliters are the same for both Q. Here's my problem, though, is if I look over here on concentration, I have a percent sign here, and I have milligrams per milliliter there. So my two concentrations that I'm expressing in the question are not in the same units. So the next step is, once you've listed C1s and Q1s and C2s and Q2s, is to make sure they're in the same units. And if they're not, you have to fix it. We don't have to fix quantities, but we have to fix our concentrations. You could have switched either. You can either change 10% into milligrams per mil, or you can change 10 milligrams per mil into percent. It does not matter, but it needs to be in the same units. So what I chose to do, and let me try to get rid of my scribbling here. Oh, where does it the first time? Is convert. Let's convert the 10% into 10 milligrams per, or I'm sorry, into milligrams per milliliter, just so that we have the same units, okay? So what I chose to do is to take my 10% and let's change the units. Because I know that 10% means 10 grams in 100 milliliters, all right? Is everyone okay with that? That equals that. Now all I need is milligrams per milliliter, not grams per liter. So I'm going to convert my grams to milligrams by multiplying it by 1,000 milligrams per gram. If I do that and then solve the math, 10 times 1,000 divided by 100, my final answer is in milligrams per milliliter. And that matches the one below. So that's what I'm going to use over here for C1. So I'm not going to use 10%. I'm going to use 100 milligrams per milliliter. Is everyone okay with that? All I did was change 10% unit-wise from 10% into the concentration of 10% expressed as 100 milligrams per milliliter. So now the units match. Now the next step is to determine your mass equations. And we said that mass is equal to C times Q. So the mass 1 is going to be my 100 milligrams per mil, which we just saw from down here. Make sure you realize that's where that's coming from. is 100 milligrams per mil times my quantity, which we said was X milliliters. Set that, oh, okay, so that's M1. M2 is equal to its C2, 10 milligrams per milliliter, times its Q2, which is 120 milliliters. This is the time to double check before we go on to make sure milliliters, milliliters, and milligrams per mil, milligrams per mil. My units are the same. So now I can move on to my next step. And that says that this, if we are diluting something, if we are just changing the volume in which a certain amount of drug exists, not the amount of drug itself, then mass doesn't change. Therefore, the mass before, M1, is going to equal M2, the mass after. All right? So since that's the formula that I have, I can substitute for that. So let's take my mass 1 from here and bring it down to there. And let's take my mass 2 from here and bring it down to there and set them equal to each other. All right? So 100 milligrams per mil times X milliliters is going to equal 10 milligrams per mil times 120 milliliters. All right? So far, so good. We've just substituted for our M1 and we've substituted for our M2. Now, this is where I will strongly recommend. The reason I've harped on you to double check your units. If you make sure that your units are the same, then do your algebra without carrying the units forward. They tend to mess you up. So let's just do the math, and we can ignore the units for now because I have double checked that my milligrams per mil concentration is the same for both, and then my milliliters are the same for both. So since the units are the same, let's just do the numbers. What is 100 times X? 100X. Set that equal to, what is 10 times 120? 1200, all right? Solve for X by dividing by 100. X equals 12. And again, then you can go back up and look at the units from what you're substituting for. X was equal to milliliters. So our answer 12 goes with milliliters. So we've determined the quantity of our 10% solution. We need 12 milliliters of a 10% solution, such that if I disperse those 12 milliliters and QS up to 120 mils, I basically get a 10 milligram per mil concentration, which is what our target was. The final answer there is 12 milliliters. Okay? Let's keep going. Same sort of thing. Let's do a different variation. I'll go a little bit quicker. It says, how many milliliters of a solution containing a concentration of 0.275 milligrams of histamine phosphate per milliliter should be used in preparing 15 milliliters of a solution that contains a 1 to 10,000 weight per volume concentration? All right? Similar to the one we did before, what was our first step? Set C1, Q1, C2, Q2. Set those up before you try to do any math. So let's look at our initial solution. Our initial solution asks for so many X milliliters, so we do not know how many milliliters, so that's why I'm going to set that one equal to X. But the solution basically had a concentration of 0.275 milligrams per milliliter, so that's where its concentration came from. Is everyone okay where my C1 and Q1 came from? Okay, the concentration was 0.275 milligrams per milliliter. That's the concentration, and I'm wanting to solve for how many milliliters of that to use. What I want to prepare, essentially, is 15 milliliters, so there's my quantity 2. Okay, and the concentration I want in the end is 1 to 10,000 weight per volume. Okay, so far so good. Just take the question and set up your C1s and Q1s and C2s and Q2s. Once you have those, what do you think the next problem is? Where do we need to go from here? Our units. So again, the nice thing is milliliters are milliliters, but again, now I have one unit in milligrams per milliliter, and I have another concentration in the ratio strength. That's not going to work. We need our concentrations to be in the same units. Do you want to go to milligrams per mil to ratio or ratio to milligrams per mil? No one likes ratio. Let's get rid of the ratio strength. So let's just re-express it. We're not changing it, but I can't deal with 1 to 10,000. It blows my mind. It's just too weird. It's a weird number, all right? But 1 to 10,000 basically just means 1 gram per 10,000 milliliters. That's all that means. So when we re-express it that way, remember, what units are we trying to get to? What we're trying to do are match these units here. So instead of grams per mil, what do I need? I need milligrams per mil. So all I have to do, again, is multiply by 1,000 to cancel grams, and I would be in milligrams per milliliter. I know it's a big funky number, but it's still just converting the units. So 1 to 10,000 means 1 gram per 10,000 milliliters. That means 1,000 milligrams per 10,000 milliliters. Just divide that out, and you see the number would be 0.1 milligrams per mil. If you divide that out, that's the same concentration, so all I have to do is substitute for that for my concentration, and now I'm in the same units. So mils and mils, milligrams per mil and milligrams per mil. My numbers are in the same units, so now I can establish what my masses are. The mass for the C1s are going to be essentially going from here across the 0.275 milligrams per mil times X milliliters. And my mass 2 is going to be 0.1 milligrams per milliliter times 15 milliliters. Again, just going across and multiplying C times Q. All right? So now we know that this is a dilution here, so M1 is equal to M2. So all I got to do is take my M1 here, substitute it down here, and take my M2 from here, substitute it down here, just set one equal to the other, and double check, are we in the same units for concentration? Are we in the same units for quantity? Yes, my units match, so I can now ignore the units and just do the math. So 0.275 times X gives me 0.275X. Equal to 0.1 times 15, that's 1.5. So to solve for X, divide both sides by 0.275, and X equals 5.45 milliliters. That's your answer. What is that? That's the quantity, that's the amount of my initial 0.275 milligrams per mil solution. If I take 5.45 milliliters of that solution and essentially basically dissolve it in the 1 to 10,000, that's what makes the final solution. So I'll drive on, but that's how you answer that question. Those are pretty easy, right? I hope. Not too bad. Those worked very much the same. This one's a lot more difficult. We're going to do the same math, but the question setup is a little more difficult. So let's go through this. It says, how many milliliters of a 16% weight per volume concentration of benzalkonium chloride should be used in preparing a 300 milliliter of stock solution such that 15 milliliters of that stock solution, when diluted to a liter, has a 1 to 5,000 concentration? All right, what the heck? That's like 3 things going on in that one sentence. There is a lot going on there. This is essentially a double dilution. We used to call them double Ds, but now that has a bad connotation. So a double dilution is when you take one solution, a certain amount of that, and you disperse it into some volume, and take some of that liquid then to make a final product. So you have 3 things going on here, and I will tell you there is no way to be able to solve this question without writing out and kind of illustrating for yourself what's happening. So let's start at the beginning. What are we starting with? We are starting with a 16% concentrated solution. So again, what I'm saying here is I'm going to use the term concentrated solution, and the 16% is coming from here, okay? So that is the first beaker I have. Do I know how many milliliters of that to use? I do not. So that's why I say I'm not sure what the quantity is, but I know I'm starting with a concentrated solution at 16% weight per volume, all right? Then what happens? I'm going to take a certain amount out of there. And I don't know how much I'm going to take out, but I'm going to use that amount and put it into another beaker. And then I'm going to add enough water to that second beaker. Do I know what the final quantity will be in that middle beaker, my stock solution? I'm going to call the second beaker the stock solution. Made from the concentrated. I started with concentrated. I'm now making my stock solution by taking some unknown amount. I don't know how many. Again, I do not know how many mils, but I know that the final amount will be 300 milliliters. So I'm going to put an unknown concentration, but a known quantity. I will have 300 milliliters of that stock solution. I don't know what the concentration is, but I got 300 mils. Then what do I do with that stock solution? What did the question say to do? How many milliliters of that stock solution? 15 milliliters is what I'm going to use. So I'm going to use 15 milliliters of that stock solution, and I'm essentially going to make, and all my arrows here and all this doesn't help a whole lot, I'm going to make essentially a final dilution that has a known concentration, 1 to 5,000, and a known quantity, 1,000 milliliters. So I know my big beaker at the end. My big final dilution concentration is going to be 1 to 5,000 concentration and 1,000 milliliters. And I also, if I work backwards, know that I'm adding 15 milliliters of my stock solution to make that. Okay? But I don't know the concentration of my stock solution. Okay? Nor do I know the amount of my concentrated solution, but I know its strength. So my point is here, we know a lot of things. So if I check mark the things we know this, and we know this, and we know this, and this. Okay? And so the trick on these double dilutions is to work backwards. Okay? The first thing you're going to do is, since we know these 2 things right here, between this and this and this, between these 3 things right here, I can solve for that. Once I know the concentration of my stock solution, then I'll know the concentration, its volume, and this concentration, and I can use these three things to solve for this, okay? So this is what I mean with a double dilution. You actually start at your final product, use that information to calculate your stock solution, and once you know your stock solution, then you can figure out how much to go back. So we'll work through it here, but the trick is to know that we're going to actually start with step one. So I'll remind you, so let's start with step one. Step one, what do we know about that? We know what our final concentration stuff is. We know that our final dilution was this, and that we're using 15 milliliters of this solution, okay? So let's just, with that in mind, let's set up our C's and Q's. It works the same way. But now I'm going to use C2Q2 and C3Q3, and the 3 represents the final dilution. The 2 is the stock solution, and we'll go back to 1 when we do our initial concentrated. So let's start with the stock solution. C2, do we know the concentration of the stock solution? No. So I set it for X. We do not know what the concentration of that stock solution is. Okay? Do we know the volume we are going to use of that stock solution? Because that's the stock solution that's going to provide the mass. The only thing that provides mass in our final dilution is what comes from the stock solution. And I said right here that we're adding 15 milliliters. So while I don't know the concentration, I know that I'm using 15 milliliters of that solution. All right? Then lastly, do I know my final concentration and my final quantity? Absolutely. So if you look over here, I know that information. I was told the final concentration will be 1 to 5,000 and that my final quantity will be 1,000 milliliters. So I know my final dilution at the end. So would you agree? I know C3 and Q3. And I know Q2. I'm just missing C2. So in one sense, there's only one variable here. However, let's do our unit check. Does milliliters match milliliters? Check. Does that percent match this? No, that's a big no check. So I've got problems with my concentration. My concentrations are not expressed in the same units. So before I go forward, let's fix one or the other. And since you all hate ratio strength, let's get rid of the ratio strength. 1 to 5,000 means 1 gram per 5,000 milliliters. We just kind of did that, so set that up, 1 gram over 5,000 mils. But since we want the percent strength, let's figure out how many grams per 100 mils, because percent means per 100, right? So how many grams per 100 mils would be my percent strength. So just set up a proportion. 1 to 5,000 is equal to X over 100. You solve for X, and it's in grams, essentially. It would be the grams that you would need for 100 mils to have the same concentration as 1 gram per 5,000. So you solve for X, you take 100 divided by 5,000. X equals 0.02 grams, but since it's that many grams per 100 mils, that's the same as 0.02%. Well, that's all I've done is re-express that C3 as a percent strength, right? So that's all we've done here. We've not changed it. We're saying that my final concentration is essentially really 0.02% concentration and 1,000 milliliters. So now that I have the same units in both places, I can determine my masses, and since I got so much scrawl there, let's just carry those down. So it should make sense that my C2, essentially, and that should be M2, but anyways, my stock solution is X percent times its 15 milliliters, all right, and my final dilution is its concentration, which we just recalculated as 0.02%, and its volume of 1,000 milliliters. Right? So I got percent, milliliters, milliliters, so I'm good there. So let's just do the math. What's 15 times X is 15X. What is 0.02 times 1,000? That's 20. So 20 divided by 15 gives me 1.3. And remember, my X was in a percent. So we just solved that my stock solution concentration. Remember, what was I solving for? I was solving for that concentration right there. I know that stock concentration now. Its concentration is 1.3%. Did we answer the question? No. We're halfway done. We now know, though, would you agree, what is the concentration of the middle section, the stock solution? 1.3%. Do we know its volume? 300 milliliters. So now we've determined that. Now we can go back to the next step. Step 2 was to use this stock solution, which we now know has 1.3%, and a volume of this. Okay, well, I know that now. And I know that what I started with was an initial concentration of my concentrated solution was 16%. So all I need to solve for is this. What I need to know is what volume of that concentrated solution would I use to make a 1.3% concentration solution that had a volume of 300 mils. So let's set those C's and Q's. All right, my initial concentration is 16%. That's my concentrated solution. I don't know how many milliliters, so that's what I'm solving for. That's what I'm going to say is equal to X. All right, but I know its concentration is 16%. All right, C2, Q2, well, we know that. That's now from these two things here. I know this and this. I can bring that up to there and say, well, the concentration of the stock solution is 1.3%, and the quantity of that stock solution I have is 300 milliliters. All right, let's do a check. Units. Check, check. Ooh, look at this, check, check. Oh, we don't even have to change the concentrations now. They match. Yay, we can kind of go forward. So let's set what our masses are. Our masses just go sideways like this, and it's just C times Q. So again, mass 1 is going to be 16 times X, and mass 2 is going to be 1.3% times 300 mils. So let's remember, since this is a dilution, mass doesn't change. So we will bring down the mass 1 here and set it over here. And we'll bring down mass 2 over here, bring it down over here, and set them equal to each other. Okay? So, units check. So 16x is going to equal to 1.3 times 300. 1.3 times 300 is 390. So what is 390 divided by 16? X would equal 24.4, and the units for X were milliliters. So that's our final mole volume, and that's our final answer. That's what goes here. So what we're saying is we need 24.4 milliliters of a 16% solution. Because if you took that 24.4 mils, put it in a beaker, added up to how much? 300 mils, shook it all up, and then of that, essentially took your 15 mils out of that and put it into 1,000 mils, gives you the 1 to 5,000 that we, 1 to 5,000 we had at the end. Okay? Let me ask you this. I know you're all like, well, okay, but did we solve both of those the same way? It was still the C times the Q equals M, and C times the Q equals M, and since it was a dilution, M equaled M, we were able to solve for it. So the way that you solve these questions have been the same every time, but in this case, in the double dilution, we had to start at the end, since we knew what the final product was supposed to be, and work backwards. All we did was work backwards to solve for things, all right? All right, let's do a weird one. This is one that I think your intuition could answer before your algebra could, but sometimes my intuition is a little faulty, but my algebra is rock solid, so I'd rather stick with my algebra. So let's see, I'm going to do this the long way. You're going to like, dude, you could have just done this. Okay, yes, probably, but let's do it my way. Let's do it the algebraic way. It will never let me down. So let's read the question. It says, if a 0.068% weight per volume concentration of methylbenzonium chloride lotion, which is kind of an antiseptic. You can see the ingredient down below there. But anyways, if that lotion is diluted with an equal volume of water, what will the percentage strength be of the dilution? So if we start with 0.068% and essentially double the volume, but don't add any drug, what is the final percentage strength? Well, you can solve this doing it the same way we've done everything. So let's just set this up. What are we starting with? We are starting with a concentration of 0.068%. Would you agree with that? That was given to us in the question. Which blows some of your mind is, were we ever told how much lotion we were starting with? What was the initial quantity, volume of that lotion? It didn't tell us. So that's why I say we have X milliliters. I have no idea what volume of that concentration I'm starting with. But I know its concentration. Its concentration is 0.068%. I just don't know the volume. So let's set the volume equal to X. Right? Anything you don't know, set it to a variable. So we don't know it. Here's the deal. What will the percent strength be after the dilution? I don't know that either. I do not know. That's what I'm solving for. What I'm actually solving for is the final concentration. But I've already used X, so I can't use X again. So what's another good variable letter? Y. So what I did is I said Y% is now equal to the concentration after the dilution. Again, I don't know it. Now here's the deal. Will I know the final quantity? When I dilute it, will I know what the actual quantity will be? No, but do I know it in terms of what I started with? If I'm starting with X milliliters, and what does it say to do? Diluted with an equal volume of water. So if I start with X and I add X, what is X plus X? 2X. So I do know the volume or the quantity after the dilution in terms of what I started with. I started with X, and I know my quantity in the end will be what? 2x. That's the trick to this question, being able to kind of set that up. But if you can visualize that, I'm starting with x amount, and if I add an equal amount to that, well, that's x plus x, that's equal to 2x. All right? So let's do our m's. Our m's are essentially, for the top one, m1 is going to be 0.068% times x, whereas my m2 will be y% times 2x. All right? Once again, this is a dilution, so the mass of one equals the mass of the other, so I'll take my mass 1 down here, and I'll take my mass 2, bring it down over here, and just say that 0.068% times x, and again, x percent milliliters, so those match. So I have 0.068x equals to y times 2x. All right? So let's just solve for that. If I multiply that on top, this right here is 0.068x, and 2x times y, if I go ahead and divide by the 2x, so let's bring that 2x book over to that side, then I'm saying that 0.068x divided by 2x equals y. That's where the algebra comes in. Are you okay with that algebra? It's not super hard, but now, what happens to the x's? Don't I have x divided by x? So the x's cancel, and really all that says is 0.068 divided by 2 is equal to y. Well, what is 0.068 divided by 2? 0.034. And again, since my x value here is in the y value here, remember here we solve for y is equal to percent, so my answer 0.034 is percent. Okay, that's the final answer. If I start with 0.068% and I double the volume without increasing any amount of drug, wouldn't you agree? Isn't it kind of intuitive? What happens to the concentration? It divides in half, and that's what we've shown, that essentially the concentration falls in half. But this was an exercise of setting up C's and Q's a little more abstract. You guys don't look like people who love abstract. Anyway, all right. Any questions on that or anything so far? Okay, let's do some acid, man. All right, so the next question says, how many milliliters of a 95% weight per weight sulfuric acid having a specific gravity of 1.82 should be used in preparing 1 liter of a 15% weight per volume acid? What do you think the trick is on this question? There's a trick here. What is the trick? It's going to work the same way with, one little additional step. My problem here is going to be concentrations, because I'm giving concentrations. They're both as percents, which is nice. That's a nice change. But they're different units. One's a percent weight per weight. One's a percent weight per volume. So again, those don't match. We're going to have to fix one or the other. All right, so I just wanted to point that out. But let's set up our C1s, Q1s, C2s, Q2s, just like we've done before. What are we starting with? We're starting with how many milliliters of the 95%. So I'm going to set my quantity of number 1 to x. I do not know how many milliliters, so that's x milliliters, but I know its concentration is 95% weight per weight. So my C1 is 95% weight per weight. My Q1 is equal to x milliliters. That's what I'm starting with. What I want to have in the end is to prepare 1 liter. So I'm going to go ahead and convert that to milliliters. 1 liter is 1,000 milliliters. So my Q2 is 1,000 milliliters. And I know the concentration that it needs to be in the end is 15% weight per volume. Okay? Any questions on how the C's and the Q's got set up? And I'm telling you, that's how you have to answer these algebraic questions. Set up the C's and Q's first. Take a moment, make sure you, and again, the units at this point don't have to match, but set up what's given to me in the question is I was given a 95% weight per weight for the concentration and unknown amount of milliliters. That's X. And I was told I want to make a 15% weight per volume concentration and a final quantity of 1,000 milliliters for 1 liter. All right? So, here's the trick to this question if you try to do it. And you can do this either way. You can either convert the 95% into a weight per volume to match the 15%, or you can convert the 15% weight per volume to a weight per weight so it matches the 95. It really works both ways. The number's a little bit funky when you convert the 95%. So it looks a little bit nicer, although you could have worked it either way. Let's convert the 15% weight per volume to a percent weight per weight. It won't be 15, but it'll be weight per weight. So let's start. What does 15% weight per volume mean? It means 15 grams per 100 milliliters, right? 15 grams per 100 milliliters. But I don't want it per 100 milliliters. I need to know, instead of a volume, what would be the equivalent weight of 100 milliliters? Yes, there'll be 100 milliliters in volume, but since I wanted weight per weight, I need the weight of that 100 milliliters. How do you convert a volume to a weight? You use the specific gravity. So all I did was start with my 100 milliliters, because that's what 15% is. It's 15 grams per 100 milliliters. My specific gravity was right here. And again, specific gravity are in the units of grams per milliliter. So if I multiply 100 by the 1.82 grams per milliliter, milliliters cancel, and that would be the weight. So essentially what's kind of cool of that solution, since it has a 1.82 specific gravity, 100 milliliters in volume actually weighs how much? 182 grams. That's the weight. Okay, if you actually weighed that volume of liquid, it would weigh 182 grams because of its specific gravity. So let's reset up that ratio. We said that 182 grams represents the weight of 100 mils, and we know that there was 15 grams of sulfuric acid because it was a 15% weight per volume. So again, now we've got a 15% weight. Well, let me just say that. We have 15 grams per that weight of 182. The problem is I do want it as a percent, and a percent is as a 100. So I don't want 15 grams over 182 grams. I need to know the proportional amount of grams over 100 grams, because that would be expressing the amount as a percent. So all I did was set up a proportion. 15 grams over my total weight of 152 is equal to some unknown weight over 100 grams. And I chose 100 grams because I wanted percent weight per weight. Okay, so when I solve for x, 15 times 100 divided by 182 numerically gives me 8.24, and that would be units of grams. That would be the grams of actual sulfuric acid in that solution. But that essentially, since it's per 100 milliliters, that's the same as 8.24%. But this is what's important now, weight per weight. I've converted it into a weight per weight. So this value now, 8.24, is what I'm going to bring back and substitute into here. So let's go ahead and do my masses. I can set my mass 1 equal to the 95% weight per weight times x milliliters. And my mass 2 is my new percent. Remember, we calculated the weight per weight. So that's the percent that's going to come up here. So my concentration is 8.24% weight per weight times 1,000 milliliters. All right. So now I can set up my proportions again, since, again, we're just diluting, mass doesn't change. So my 95% times x milliliters is going to equal to my 8.24% times 1,000 milliliters. And do a quick check. My percents are percents, and they're in the same units, weight per weight, volumes and milliliters, so I can ignore the numbers. So multiply 95 times x gives me 95x. 8.24 times 1,000 gives me 8,240. Divide both sides by 95, and you get a total final answer of 86.7 milliliters. All right, so I need 86.7 milliliters of the 95% sulfuric acid. If I dilute that amount up to a liter, I will get a final concentration of 15% weight per volume. All right, we're almost done. We got 2 more questions to do, but we're going to change topics here a little bit. We've been diluting. And the trick with diluting is that, other than diluting myself, but anyways, the point of dilution is that the mass doesn't change. As you add water or dilute things, the mass doesn't change, though the concentration does. Fortification is different. Fortification is when you start with a certain concentration and quantity, you start with a certain mass, and you add both mass and quantity to it. So the point is here, what we're doing with fortification is we start with an initial mass of the drug. We add mass to it, and we get a final combination of the mass, all right? Meaning that mass 1 plus mass 2 is going to equal mass 3, all right? So we start with something, we add something that has drug with it, so that the mass increases, and we can determine what the final combination, the final total mass is going to be after we've combined those, okay? All I really want to make sure you understand is that the formula for mass doesn't change. So C times Q1 plus C times Q2 is going to equal C3 times Q3, okay? So we're still going to do C's and Q's, but now we're going to be adding an ingredient that has mass to it as well. So that's why it will be changing. The mass changes in these examples with fortification, all right? So let's just use this example, all right? It says a pharmacist intends to fortify meaning add drug strength to 10 grams of a 0.1% weight per weight tacrolimus or protopic ointment by adding 12.5 grams of an ointment containing 0.03% weight per weight of tacrolimus. By combining those amounts of those two tubes. So basically what we're doing is that we're going to start with this tube right here, because here's a 10, essentially we're starting with a 10 gram tube of 0.1%. And what we're going to do is we're going to squish out some of this stuff and we're going to add it to that tube. All right, so we're going to take a certain amount of this stuff here. Will the stuff from the 0.03% protopic have drug in it? Yes, it's got drug in it. Does it also have diluent though? It's not just pure drug, right? So you're changing the overall weight, but you're also adding part of that weight is drug. So now we're changing the mass of the drug. We're not just diluting it, all right? So let's do our C's and Q's. This is pretty straightforward. What are we starting with? We're going to start with 10 grams, right there, of what strength? 0.1% tacrolimus. Is everyone okay with that? That's this tube right down here. So that this is our tube here, right here, 10 grams of that tube. Right? Then, what are we doing next? We are then going to mix it with 12.5, I wanted a different color. 12.5 grams of the 0.03%. All right? So that weight, 12.5 grams of 0.03%. So that should be pretty straightforward. All of that information was given to us. My question to you is, when we mix all of those together, we will get what concentration? I don't know. That's what we're solving for. It wants to know what would the percent strength be, so what would the final percent be, so that's why C3 is X. We don't know what the combined concentration will be. Let me ask you this. Will you know what the combined quantity would be? I want to make sure you understand. Quantity doesn't matter, doesn't just appear out of nowhere. If I started with a 10 gram tube, and then I add 12.5 grams, what's the final quantity? 22.5. The weights are additive. So you do know the Q3. Even if you don't know its concentration, you know Q3 is going to be the sum of its two parts. So the Q3 is essentially 22.5. Because of that, we can determine our masses just going sideways again. You can say that essentially the mass for each of those situations is its concentration times its quantity. So let's set up the formulas. Now remember, didn't we just add drug as well as diluent to our first thing? So now the mass is changing. And all you need to do when mass changes, when you fortify something, is you take the initial mass, you add the second mass, and that's going to equal your final mass. M1 plus M2 equals M3. So to do that, all you got to do is say, okay, let me see if I can stick with my color combination here. This mass that I started with is down here. To that, I'm going to add this mass. So there's that mass. And what I'm going to get in the end is this final, okay? So by doing that, I can say, check my units, don't do anything, percent, percent, percent. We're good. Grams, grams, grams. Okay, my units are all the same across all three mass units, so now we can just do math. So what is 0.1 times 10? 1. What is 0.03 times 12.5? That's essentially 0.375. Set that equal to x times 22.5. That's 22.5x. So again, add 1.375 divided by 22.5, solve for that, and I get 0.06. And I'll remind you, my x was expressed as a percent, so that value is in the units of percent. So when I combine all that stuff together, I get 0.06%. All right? Any questions? I'll give you a hint. When you take a high strength and you add a low strength, again, in this case, the high strength was 0.1%, the low strength was 0.03%. When you mix those together in any amounts, your answer needs to be where? Somewhere between the two, okay? When you take a high strength and a low strength and mix them together, you get something in the middle, okay? Where in the middle will depend on the relative amounts, but when you combine two things together of different strengths, what you get in the mixture will be something with a concentration between those two. So as a quick double check. That's the whole point of the allegation stuff we're going to do next lab, God forbid, next class. All right, ready for the last question? Oh yeah, you look ready. Let's do some zinc oxide. So this is the little cream that you see the lifeguards put on their nose as a sunblock, if you will. We can put it on babies' bottoms to protect them as well. So either way, it says how many grams of zinc oxide, now this is the zinc oxide powder, should be added to 3,200 grams, 3,200 grams of an existing, we already got a zinc oxide ointment, it's 5%. And I've got 3,200 grams of that ointment. But I want to add additional drug, that is zinc oxide, so that my final ointment in the end is 20% weight per weight of zinc oxide. right? We're fortifying. We're taking a 5% concentration of ointment and making it a 20% ointment. Would you agree the mass is going to change? There's going to be more drug afterwards than there was to begin with, all right? So the only little bit of a trick to this is when our C's and our Q's, we're going to do it the same way. When we use a bulk powder, what concentration is zinc oxide powder? If it's zinc oxide powder, it's 100%. I mean, it's all zinc oxide powder. And not every ingredient is that way, but if you're adding a bulk powder of something like zinc oxide, you're weighing zinc oxide, and the only thing you're weighing is zinc oxide, then its concentration is 100%. So in that case, we would say that the concentration of the zinc oxide powder we're adding is 100%. All right, it is 100% weight per weight. Everything I weigh of zinc oxide is zinc oxide, so it's 100%. How much of that we want to use? I don't know. It says how many grams. So I'm going to set the quantity of that powder equal to X. I don't know. X grams of this 100% powder is what I'm adding. What are you adding it to? You are adding it to an ointment that has a concentration of 5%, all right, and that you already know you already have 3,200 grams. All right? So far, so good? Should be easy. What am I making? In the end, when I add those two things together, the final concentration I want to be is 20%. All right, there it is. Here's the trick. If there's any difficulty for some people at this point, remember how I said quantities are additive. All right? We can predict what the final quantity will be, because how much of that ointment am I starting with? 3,200 grams, right? And aren't I just adding to it? How much weight am I going to add to that ointment? X grams of zinc oxide. And while I don't know what it is, I'm going to say that amount is X grams. So essentially, remember we said Q1 plus Q2 is equal to Q3. So 3,200 grams plus X grams is the total quantity for Q3. Okay? That's what makes this a little bit more algebraically, because now we can solve for our masses. They should be pretty straightforward, except for this one is a little tricky for some people. Again, C1 is 100 times X. C2 is 5% times 3,200. Those are pretty straightforward. Mass 3, I should have said masses there. Mass 3 is the 20% concentration times its quantity, which is 3,200 grams plus X grams. All right, don't forget that. It's that quantity. So this is kind of what I'm saying is a little bit trickier. That Q, you need to carry that over. Now, just solving it, though, is pretty straightforward. Let's pull down the masses. My initial mass is 100% times X grams plus the 5% times the 3,200 grams. Those are my two ingredients. That's going to equal my final concentration 20% times its quantity of 3,200 plus X. Check my units, percent, grams, 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 so I don't have to mess with that. So what is 100 times X? 100X. Plus, what is 5 times 3,200? 16,000. Okay, no magic there. Make sure you can do this. This is where make sure. So to multiply this part, you got to take the 20% times the first number and 20% times the second number. So when you multiply that together, you get 20 times 3,200, which is 64,000, plus 20 times X, which is 20X. All right, so make sure you can get this out of that. All right, just make sure you're okay with that. Now it's a simple algebra section. Let's just subtract 20X. So if I subtract 20X there, and subtract 20X there, I get 80X. And again, if I move this over to here, 64,000 minus 16,000 is 48,000. Solve for X divided by 80, and you get 600 grams. The fact that your guys are packing up means that hopefully that algebra is straightforward, and most of you, I'm sure it is. But again, some of you, anyone, Wichita as well, if you're reviewing these problems and have some struggles with the algebra stuff, the formulas will always be set up this way. Please let me know, because next week we're going to do the same kind of calculations and do them in a different way using the alligation method.